Welcome to today's deep dive. It's great to have you with us. You know, when you watch a live news broadcast and there's that like awkward 2-second pause after the anchor in the studio asks a
Oh,
question?
yeah, and the reporter out in the field just kind of stares blankly at the camera for a second before finally answering.
Exactly. You're watching them in your present, but they are reacting to a past that just hasn't quite reached them yet,
Mm.
because of the satellite delay.
Right, the signal literally takes time to travel.
Yeah, and that delay is actually the perfect entry point for what we are unpacking today. I mean, we expect the universe to be perfectly synced up, almost like a well-edited movie where everyone is experiencing the exact same now.
But when you really look at the fundamental physics of reality, that perfectly synced movie is, well, it's a complete illusion.
It really is. So today we're diving into this fascinating, highly analytical, and frankly quite rebellious series of blog posts called Einstein's Slacking.
It's just a phenomenal, incredibly dense piece of writing.
Oh, dense is the word for it. We are specifically zeroing in on piece number 139, which is titled Positional Relationship of the Window Surface. It's written by a blogger who goes by the name Zionod2023.
Right.
Our mission today is to explore this author's radical geometric critique of how we visualize space, time, and, the speed of light.
Mm.
And just to set the stage for you, the author isn't just writing out complex equations.
No, they're actually using 3D modeling software.
Yes, specifically Blender. They use it to challenge the spatial assumptions of literal historical geniuses like Albert Einstein and Roger Penrose, while also championing the older, kind of more intuitive ideas of Hendrik Lorentz.
The core theme we're dealing with here really boils down to a debate between two concepts in physics, which are proximity action versus action at a distance.
Okay, let's unpack this because right out of the gate, action at a distance sounds a bit, I don't know, like magic.
It kind of is, yeah. This entire deep dive centers on a simple but profound concept, which is information delay. We are going to explore how the time it takes light to travel from an object to our eyes fundamentally distorts our entire perception of reality.
Right, so what does the author actually mean by action at a distance, and why are they using 3D modeling software to argue against it?
Well, to understand the author's critique, we really have to look at the metaphor they use for how theoretical physicists usually operate.
Oh, the king metaphor, right.
Yes, the author says physicists who rely purely on abstract math are like a king sitting safely in a castle looking down at a static map on a table.
Just moving little pieces around.
Exactly. The king sees the little wooden blocks representing armies and thinks he understands the exact state of the battlefield at that very moment.
So the king assumes that moving a piece on the board instantly reflects reality. That's the action at a distance, right? Like assuming information teleports instantly from the battlefield to the map.
Precisely. But the king is entirely forgetting about the information officer.
That's
Right. In reality, there is a person on a horse who has to gather the battlefield reports, ride across the terrain, and physically hand that report to the king.
and that takes time.
A lot of time. By the time the king receives the report and moves a wooden block, the actual army on the actual battlefield has already moved somewhere else. So the king's map is fundamentally a lie because it ignores the travel time of the information.
That makes a lot of sense. But, like, how does this apply to standard physics? Are physicists really ignoring that travel time?
The author argues that they are, yeah. When you map a 3D universe onto a 2D Cartesian plane,
Like a standard flat graph with an x and y axis?
exactly, you plot coordinates and assume you can observe all those points simultaneously from a top-down, God's eye view. The author calls this a mathematical fantasy
Wow, a mathematical fantasy.
because it ignores the physical reality that light has to travel through space and hit an observer's retina. That physical travel is proximity action. Things only interact when they physically touch, or when a wave physically reaches them.
You know, when I was reading this part of the source, it instantly made me think of playing an online multiplayer video game.
Oh, absolutely. The author actually mentions this. Video games and something called deviation shooting.
Yeah. Think about it. If you're playing a shooter game online and you aim your crosshairs exactly where a running player is currently rendered on your screen, you are going to miss.
Because of server lag.
Right, because of server lag. It takes a few milliseconds for the server to tell your computer where that player actually is. To hit them, you have to use deviation shooting. You have to shoot slightly ahead of their avatar, aiming for where they will be when your bullet data reaches the server.
A very apt comparison.
The author is basically saying Einstein and Penrose forgot about the universe's server lag.
That analogy captures the essence perfectly. The universe has a ping rate. And, humanity actually discovered this server lag a lot earlier than you might think.
Yeah, the author grounds this argument chronologically, starting way back in 1676 with a Danish astronomer named Ole Rummer.
Right, 1676.
Centuries before we had 3D modeling software or video games, this guy is out there figuring out the ping rate of the solar system. The source mentions he did this by staring at Jupiter's moon, Io. But how do you calculate the speed of light just by looking at a moon?
Well, Romer was observing Io eclipsing, which means he was timing exactly how long it took for the moon to pass behind Jupiter and emerge on the other side.
Okay.
And he noticed a variance that just shouldn't exist if the universe was perfectly synced up. The author lays out the specific numbers from Romer's data.
What were the numbers?
So when Earth was in its orbit moving toward Jupiter, say around the spring equinox, the time Io was hidden behind Jupiter appeared to be shorter. But when Earth was moving away from Jupiter around the autumn equinox, the eclipse seemed to take longer.
I want to make sure I'm visualizing this correctly. Is it kind of like running into waves at the beach?
How do you mean?
Like if I run into the ocean, the waves hit my chest faster, one after another. But if I turn around and run back toward the sand, the waves take longer to catch up and hit me.
That is an excellent way to picture it, actually. Romer realized that the Earth was literally running toward or running away from the light waves, carrying the visual image of Io's eclipse.
And the source notes that this information delay varied pretty significantly, right?
Yeah, it varied from 900 seconds to 1100 seconds, purely depending on Earth's position and movement relative to Jupiter.
Wow.
Romer used this variance to prove that light wasn't instantaneous.
And he actually calculated a speed from that, right?
He did, yeah. He
Okay.
estimated it at roughly 210,000 to 220,000 kilometers per second.
Which is astonishingly close to the actual speed of about 300,000 kilometers per second, especially considering he was doing this with, like, 17th century telescopes and a quill pen.
If we connect this to the bigger picture, it was a massive paradigm shift for science.
Oh, for sure.
Up until then, giants like Isaac Newton thought gravity and light might be instantaneous actions at a distance. Sort of faraway magic.
Right.
But Romer proved light is a physical thing. It's an information officer galloping across the solar system, and it takes time to arise.
So Romer proves light has a speed limit across the massive distances of the solar system. But how does that actually distort our vision here on Earth, on a smaller scale?
That brings us to the next historical figure the author introduces, which is James Bradley.
Ah, right. He realized this solar system server lag literally bends the light coming into his telescope.
Yes, James Bradley discovered something called stellar aberration. Because the Earth is moving through space so quickly, Bradley found he had to physically tilt his telescope slightly forward to catch starlight.
To catch the light.
Exactly. The author uses this to show that movement alters the angle of incoming information.
The source used an umbrella analogy for this that really helped me, actually.
The rain one.
Yeah. If you are standing still in the rain, you hold your umbrella straight up. But if you start sprinting through the rain, you have to tilt the umbrella forward so the raindrops can make it down without hitting your legs.
That's a great way to think about it.
So Bradley had to tilt his telescope so the raindrops of light could make it all the way down the tube to his eye while the Earth was moving.
And that physical reality of the tilted telescope is where the author brings in Blender, the 3D modeling software, to introduce a really mind-bending geometric concept. They move away from the abstract God's eye map and focus entirely on what they call the camera eye.
The camera eye.
Right, the literal physical point of observation.
And this is where the author introduces a concept called the window surface, or madamen in Japanese. But I have to admit, when the source started talking about the exact coordinate geometry of this telescope in Blender, I got a bit lost.
It gets very technical.
It really does. Can you break down why this window surface matters, like geometrically?
Let's remove the complex coordinates for a second. Just use a physical analogy.
Yeah.
So imagine the observer's eye, the camera eye, is at a coordinate of y equals -10, and the telescope's objective lens is at y equals 0.
Okay, tracking so far.
The author points out that light hitting the top of the telescope, say at coordinate 1, 0, 10, and the bottom of the telescope at 0, 0, 0, reach the observer's retina with different pass degrees.
Wait, so if I'm looking at a 10-meter-long telescope, the top of it and the bottom of it exist in different moments of the past from my perspective.
Yes, because of the information officer. Think of every single photon of light bouncing off that telescope as a messenger.
Okay.
The messenger from the far end of the telescope has a 10-meter head start, basically, so it takes slightly longer to reach you.
Right, it has further to travel.
Exactly. The messenger from the edge nearest your face has almost no distance to travel. But your eye, your camera eye, receives both messengers at the exact same time.
Okay, so it's like hearing the thunder after seeing the lightning, but on a microscopic scale for human vision.
That's a good comparison.
My eye is taking light from the far end of the telescope, which is slightly older, and mashing it together with light from the near end, which is slightly newer.
Yes. You are perceiving a temporal Frankenstein. Even though the telescope is one solid object in the present, your brain is stitching together an image made of different timestamps. The object you perceive is made of varying past degrees.
So where does the window surface come into play? Why do we need a new term for this? Like, can't we just calculate the distance from the object directly to the eye and be done with it?
The author argues that you need a middleman to do honest physics. The window surface is an invisible intermediary 2D plane sitting right in front of your camera eye.
Like at y equals -9, just before it hits my eye at -10.
Exactly. It's like a pane of glass you're looking through. To truly map reality, you have to account for the object as it exists in 3D space, calculate the exact staggered moments, the delayed light from every part of that object passes through that 2D window surface, and then the final moment it hits your retina. If you just draw a tilted line on a graph and ignore that literal bottleneck of light delay, you are lying to yourself.
Here's where it gets really interesting, because this brings us to the climax of the source material. The author takes this concept of the camera eye and the window surface and uses it to completely tear into Einstein's special relativity and Roger Penrose's models.
They do not hold back.
Not at all, which is wild because special relativity is the bedrock of modern physics. What exactly is their problem with Einstein?
Well, the author's central claim is that Einstein and Penrose are math-obsessed.
Math-obsessed.
Right. By focusing entirely on creating elegant, symmetrical mathematical equations, they ignored the gritty, messy physical reality of the information officer and the camera eye. The author actually accuses them of being trapped in a Ptolemaic-level trick.
Oh man, comparing Einstein to Ptolemy is a massive insult in the physics community.
It really is.
For a little context for you listening, Ptolemy was the ancient astronomer who created these insanely complex mathematical formulas called epicycles, basically drawing circles within circles to prove that the sun and planets revolved around the Earth.
Right, a geocentric model.
And the math technically worked to predict where planets would appear in the sky, but the underlying physical assumption was completely, totally wrong. The author is saying Einstein did the exact same thing.
Yes. And to understand why, we have to look at the physicist the author actually championed, Hendrik Lorentz.
Okay, Lorentz.
Lorentz thought deeply about local physical perspectives. Let's use a thought experiment. Imagine you are inside a futuristic train moving at 0.6 c, so 60% the speed of light.
Okay, I'm on the train, moving very, very fast.
If you shine a flashlight forward, Lorentz understood that from your local physical perspective, the apparent speed of that light should change depending on which direction you measure it.
Because I'm moving.
Right. If you measure a light that is trying to catch up to you from behind, the relative speed is slower. It might look like 0.4 c, which is just 1.0 minus your 0.6 speed.
Got it.
Or if you measure it on the y-axis, perpendicular to your movement, the source shifts, the math works out to 0.8 c, because 0.6 squared plus 0.8 squared equals 1.0.
Okay, that makes perfect intuitive sense. I am physically moving through the ping rate of the universe, so the light waves are going to hit me at different relative speeds depending on my movement. That's the server lag in action.
That was Lorentz's view. But Einstein's special relativity flipped this entirely. Einstein's math defined the speed of light as a constant c in all directions for the moving observer.
Really? What?
Yeah. Whether you are standing still or on a train moving at 60% the speed of light, Einstein said that light will always approach you at exactly 300,000 kilometers per second. Period.
But wait, how is that physically possible? If I'm running away from the light, it has to hit me slower. How did Einstein make the math work to keep the speed of light constant?
He had to invent new concepts. To keep the speed of light constant in his equations, Einstein theorized that space and time themselves must bend and warp. He introduced things like length contraction, the idea that objects physically shrink as they move faster, and time dilation, where time literally slows down.
Ah, and here's where the Ptolemaic level trick comes in. The author is saying that length contraction and time dilation are modern-day epicycles. They are mathematical band-aids.
That's their argument, yes.
The author believes Einstein just couldn't accept that the apparent speed of light changes based on the observer's movement, so he warped the entire universe on paper to protect his equations.
Now, just to maintain a calm, objective tone here, we should emphasize that this is the author's passionate geometric argument. It is not an endorsed scientific consensus. But they are arguing that Einstein threw away the physical reality of the observer. He threw away the window surface.
Right.
The author believes that Rummer, Bradley, and Lorentz actually respected the information officer. They respected the physical delay of light arriving at the actual local camera eye.
The source goes pretty deep into Roger Penrose here, too. They critique something called the Penrose-Terrell rotation. What is that, and how does it fit into this attack on modern physics?
So, the Penrose-Terrell rotation is a famous concept designed to explain what happens to an object moving past you near the speed of light. Instead of looking squished, like Einstein's length contraction suggests, Penrose's math showed that the object would appear rotated.
Rotated?
Yeah. But the author insists this is just more Ptolemaic math. They argue that Penrose is manipulating equations on a 2D plane to create this rotation effect, instead of calculating the true, messy 3D delay of light hitting a localized camera eye.
I have to say, looking at the Blender models the author provided in the source, it is a really compelling visual argument.
It really is striking to look at.
They show a purple sphere moving and a blue sphere observing it. And they visually demonstrate that if you don't account for the changing distance and the light delay of every single pixel hitting that window surface, your math is just fundamentally misrepresenting what a human being would actually see.
And this is why it's such a valuable read. It forces us to confront our blind spots. The author is demanding we don't just accept elegant math blindly. We have to constantly ask, what is the physical mechanism of observation?
Right. You can't just write a beautiful equation on a chalkboard. You have to remember that the light bouncing off the chalkboard takes actual time to reach the student in the back row.
Exactly.
The map is not the territory. It's a heavy critique. And whether you agree with their takedown of Einstein or not, it fundamentally shifts how you think about something as simple as looking around a room.
It changes everything.
When you look up at the stars tonight, or honestly, even when you just look at the person sitting across from you at a coffee shop, you aren't seeing the universe as a unified now.
No, you're not.
You aren't seeing them in the present. You are a camera eye, processing a chaotic, delayed stream of pasts.
The author warns us about confusing the map for the territory. But it really makes you wonder if our brains are constantly stitching together delayed light to create the illusion of a smooth, continuous present. Are we all just information officers living in our own slightly delayed, custom-built versions of reality?
That is going to keep me up at night. The next time I see a live news broadcast glitch out, I'm not going to just think about satellite issues. I'm going to think about the window surface and how none of us are ever truly sharing the exact same present moment. Thank you so much for joining us on this deep dive into the source material. We'll catch you on the next one.